Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture 60 of the course Theory of Computation. Right. In this week 12, we have been seeing various aspects of space complexity. First, we defined space complexity. We saw the relation and connection between space complexity measures and time complexity measures. Then we saw NL completeness, right? Then we saw Savage's theorem in the previous lecture. In this lecture, I'll just summarize I'll just quickly go over some of the other topics that appear in this chapter in the SIPSA book, because we do not have the time in the rest of the time that I have in this course. We do not have the time to completely cover these topics. So what I will do is, whatever the remaining main two topics are there, these two main topics, we will just give an overview of these two main topics. So I'll explain what these results are and what they are about, and hopefully this will help you get some perspective, so that in case you are interested, you can go and read those topics yourself, right? Or refer to other wonderful resources like videos by other people or which explain these topics, right? So the first thing that I want to talk about is this result that states that NL equal to co-NL, right? So this is one of the topics. But before saying NL equal to co-NL, I should first say what is co-NL, right? So you may remember we defined this term called co-Turing recognizable, right? So this was sometime in chapter 3 or chapter 4, I think. Co-Turing recognizable, a language is said to be co-Turing recognizable if its complement is Turing recognizable. So co stands for complement. It is similar here. So co-NL, a language is said to be in co-NL if its complement is in NL, right? So that is the definition of co-NL, right? So similarly, we can define co-NP, the set of languages whose complement are in NP, right? So while I didn't mention this in this course, NP and co-NP we don't know the relation between them, meaning both of them contain P. So it's something like this, right? So if this is NP, this is co-NP, right? We know that P is contained here, the intersection of NP and co-NP, but we don't know any other relation between NP and co-NP. What I want to say is, like it is not clear whether it is not clear what the relation is. So there are two possibilities. One is that NP and co-NP could be equal, or it could be that P is equal to the intersection of NP and co-NP, right? But if one of them is shown to be the subset of the other, let's say if NP is shown to be the subset of the other, then it follows that they are equal, right? That it's not that hard to see, but because we haven't covered those topics, I will not get into that, right? So this is what we know. Like in the case of time complexity, NP and co-NP are not the same, or are not known to be the same. They may be the same, but it is not known, right? So in some sense, we can think of NL and co-NL as some kind of parallel to NP and co-NP, right? Because it's like you have a language, you have a non-deterministic class and the complement of its, and the complement class, right? It is not the complement of NP, right? Again, NL is not the complement of, co-NL is not the complement of NL. Rather, it is a set of languages whose complement is in NL, right? Similarly, co-NP is not the complement of NP. It is a class of languages whose complement is in NP, right? So in the case of time complexity, we don't know what the relation is. But in the case of space complexity, right? So there was yet another surprise, which was that NL and co-NL are the same. This was proved in 1987 by two independent efforts by Neil Emmerman and Robert Serafini, right? So this was somewhat surprising, right? And this was shown by proving that so we saw that path is an NL complete language, right? Path was an NL complete language. So what the proof does is to show that the complement of path is in NL, right? This implies that since the complement of path is in NL, since path is NL complete, we know that the complement of path is co-NL complete, right? Anything in co-NL can reduce to path complement, right? So again, I have not defined what is co-NL complete, but it is defined exactly like NL complete, but with the complement. So the fact that path complement is in NL and path complement is in co-NL complete implies that anything in co-NL is contained in NL, right? So this gives us that co-NL is contained in NL, and the same argument can be flipped, because path complement is in NL implies that path is in co-NL, and we know path is NL complete. This gives us that NL is in co-NL, right? So we have co-NL is in NL, contained in NL, and NL is contained in co-NL. Together we get that NL is equal to co-NL, right? So that is the very, very high level picture of the proof, right? So we need to actually, so to show that, so think about it. Like we saw several examples, right, of non-deterministic like languages in NP. Like you want to show that there is a subset with a certain sum, you can demonstrate the subset, and it can be verified that it has the certain sum. Or you want to show a graph is 3 colorable, you can demonstrate a coloring, and then you can verify that it is indeed a 3 coloring. But here the problem is difficult. So like we saw path is in NL, where we kind of verify that there is a path. But here we have to verify that there is no path. So now you may be appreciating the difficulty. When something, like, to verify that something is there is easy. You can guess that and verify it. Like this graph is 3 colorable. Okay, so you guess the 3 coloring, and if it happens to be correct, you can verify it. Now you have to verify something is not there, the non-existence of a path. How do you verify that there is no path from S to T, right? You cannot guess a non-path, right? That there could be another sequence of vertices which is an actual path, right? So this is the tricky part. How do you guess something and verify something which actually tantamounts to a proof that there is no path from S to T? That happens to be the tricky part. And what the proof does is to actually determine the number of paths, a number of vertices that can be reached from S, right? So suppose the graph has 100 vertices, right? Suppose the graph has, let's say 100 vertices, and and let's say only 65 of them are reachable, right? So this 65 reachable from S. Of course, this will contain S itself. S is kind of trivially reachable from itself. So you first determine this number 65, and then you guess each of these 65 vertices and verify each of these 65 vertices are indeed reachable, and also ensure that none of them is T. Right? So we know that there are 65 vertices reachable. We guess 65 vertices, verify each one of them, and verify that all of them are reachable from S, and also verify that none of them are T. So now we know that 65 vertices are reachable. We verified 65 vertices that are not T, they are all reachable from S. So it has to be the case that T is not reachable, right? So this is how we end up providing a proof that T is not reachable. So this also involves multiple steps. First, we have to determine the number of reachable vertices. That is also not easy, because remember, we only have log space. We have non-determinism, but we only have log space. So determining the number of reachable vertices, or in this example, the number 65, that itself is not so straightforward, right? So we have to kind of slowly build that number, and once we have that number, how do we actually verify that or you cannot have a list of the vertices reachable from S, because that list itself will not be logarithmic in size, right? So that could be linear in size. So you have to be clever in doing all of this, but this is the high level picture, right? So that is the way we prove that NL is equal to co-NL, by giving a certificate that a vertex T is not reachable from a vertex S by this circumptuous route, right? Or, I wouldn't say circumptuous because it's a difficult task. So any route is going to be hard, right? So that is, and again, it was a surprising result that NL and co-NL are the same, because one of the kind of similar set of classes that we have in time complexity, P and NP, NP and co-NP, we don't know of such a result, right? So this is one result. The next thing I want to talk about is P space completeness. So we talked about NL completeness. So now similarly we can talk about the hardest problems in P space. P space is the class of all languages that can be decided in deterministic polynomial space. And because of Savage's theorem, this is also the same as non-deterministic polynomial space, right? So non-deterministic space n power k is contained in deterministic space n power 2k. So if it's polynomial non-deterministic and polynomial deterministic space are both the same, right? So that is P space. For example, SAT is in deterministic space n, breadth first search is in deterministic space n, the way we do it. And we also know, like I already mentioned, that P space is equal to the non-deterministic polynomial space, right? And one small fact is that we know that L is not contained in P space. L is not that is not contained. L is a strict subset or a proper subset of P space, right? L is log space and P is P space. This is a proper subset, meaning we know that there are languages that are in P space but are not in L, meaning there are languages that require more than logarithmic space but less than polynomial space, right? We know that there are such languages. This is by something called space hierarchy theorem. Okay, so which again is another topic that I will not cover. Space hierarchy theorem basically says that if you have two functions, let's say n cubed and n squared, right? So n cubed is clearly bigger than n squared, even meaning limit n cubed divided by n squared, right? It tends to infinity. So if you have two such functions, one clearly faster growing than the other, not by a constant, it has to be even bigger than a constant, then there is a language that requires n cubed space but cannot be decided in n squared space. So basically, whenever there are two functions, one of which is much faster growing than the other, there is a language that requires the bigger space and cannot be decided in the smaller space, right? So maybe before I forget, I'll just write down a listing of languages that we or the classes that we know. Okay. Classes ordering that we know. Right. So L is the smallest. L is contained in NL, right, which is equal to co-NL. And NL is contained in P, which is contained in NP, which is also actually contained in co-NP, but we don't know, like NP, between NP and co-NP there is no such thing, right? It may be equal but we don't know. P is also contained in co-NP, and both of these are contained in there are other things which I will skip, but all of this is going to be contained in P space, which is also the non-deterministic P space. This is just like ordering of the classes that we know. And the thing is that all of these inclusions, right, containments, we don't know whether it is proper or not. We don't know if there is a language that is in NL but not in L. We don't know if there is a language in P but not in NL. We don't know if there is a language in NP but not in P. We don't know P versus NP. Right? We don't know P versus co-NP. Right? So all of this we do not know. We don't know whether P is how P and P space are related. We don't know how NP and P space are related. Is there a language in P space but not in NP? We don't know. The only thing that we know, however, is this. Out of all these classes, there are some things that I have listed to be equal: NL, co-NL, and P space and P space. The only other thing that we know is L is not equal to P space. Right? That's what I mentioned. Because of space hierarchy theorem, L is not equal to P space. Meaning there are languages in P space but not in L. So just think about it. You have a sequence of sets, this contained in this contained in this contained in this, and so on. So, but we know that the leftmost and the rightmost are different. So it cannot be that all of these are equal. There has to be some two sets or some two classes here which, like, either L is not equal to NL, or NL not equal to P, or P not equal to NP, or NP not equal to P space, right? If all of them are equal, then L will be equal to P space. So but we don't know which one is not equal. Maybe all of them are not equal. But all of them cannot be equal, but all of them can be not equal. Because if all of them are equal, then that would mean L equal to P space. But all of them can be not equal. That is possible, right? So this just to give you a perspective of what all classes we have learned so far and how they kind of relate with each other, right? Anyway, so now let me come back to the P space, that discussion that I was talking about. So we know that L is in P space but not equal to P space. Anyway, so P space completeness is similar to NP completeness or NL completeness. So B is P space complete if B is in P space and all the languages in P space are reducible to B. And in P space completeness we use polynomial time reduction. Okay, so this is something that you have to keep in mind: polynomial time reduction. In NP completeness we use polynomial time reduction. In NL completeness we use log space reduction. Right? So everywhere we want the reduction to be a bit weaker than the class. So in NP completeness we want it slightly lower. So instead of NP we use polynomial time. In NL completeness, instead of NL we use logarithmic space, not the non-deterministic one but the deterministic one. In the polynomial space completeness we use a bit lower, which is polynomial time. Right? So this is the definition of P space completeness. So these are kind of the hardest problems in P space. I'll just briefly explain few P space complete languages and and summarize. Right? So one of them is TQBF, right? Otherwise known as true fully quantified Boolean formula. So it's a Boolean formula with quantifiers. So for instance, let's say there is a Boolean formula like satisfiability can be written as does there exist an x1, does there exist an x2 such that, does there exist an xn such that phi of x1, x2 etc xn is true. So basically we are asking whether there is some assignment x1, x2 such that a formula evaluates it true, right? So this is sat. But now what if we allow both quantifiers? So instead of does there exist, we also include, let's say, for all, the for all quantifier, and we ask questions like this: for all x1 does there exist an x2 such that does there exist an x3 such that for all x4, and so on, and some other formula psi of x1, x2 etc. this is equal to true, right? These type of questions where where there is a quantifier. So quantifier means these things. Quantifier means there exists and for all. There exists is called the existential quantifier, and for all is called the universal quantifier. So you want to quantify each of these variables. All the variables have to be quantified. That's why it's called fully quantified Boolean formula. Right? So it has to be a true fully quantified Boolean formula. Right? So that is one language which is p-space complete. The second one is a bit more fun or a bit easy to understand. So think of a game where I say a name of a place. Let's say I say Hyderabad. Now you have to name a place which starts with the last letter of the place that I mentioned. So I said Hyderabad. So maybe next you have to start with D. So you can say Dubai or you can say Delhi. Now you say Delhi, then I have to name a place that starts with an I. Let's say I say India. Then you say A for Austria. Right? So then again A for, let's say, Afghanistan. Then N, you say Netherlands. Right? So like that it goes. The only rule is that we should not repeat a place that is already said. Right? And it has to be a valid name of a place. Right? So this game in the general sense is p-space complete. So you may be wondering, what is this okay, very specific game? How can this be p-space complete? So that's what I said. This is just to illustrate the game. In general, it is like you have a graph, right? So you have a graph like what we have here, and player one will pick, like player one will start, right? So player one will say will take an arrow, and player two has to take an arrow from there, right? And whoever cannot have a next turn loses. So for example, in this game that is drawn here, player one actually loses, because player one, suppose player one takes this way, he goes to 3. Right? Now player 2 can let's say go to 6. So this is 1, this is 2, right? Player 2 can go to 6, and now player 1 cannot go, there is no outgoing arrow, right? If player 1 had taken this way, right, he went to 2. Now player 2 can do this, he can go to 4. Right. Now player 1 has only 2 options, either go to 5 or go to 7. So suppose he goes to 5, now player 2 goes to 6 and player 1 is stuck, right? Now player 1, if he had taken this way to 7, then player 2 can go to 9 and again player 1 is stuck. So now you see, whichever step player 1 takes, player 2 has an answer by which he will eventually end up cornering player 1. So in this particular layout, player 1 does not have a winning strategy. Right? So this is a simple game that is easy to describe. So if player 2 can always win or has a strategy to always win, player 1 cannot have a strategy to always win. What I am saying is, here there is a strategy for player 2 to always win. Right? So whatever the first move that player 1 does, either this or this, player 2 has a response by which eventually he will corner player 1. So if player 1 takes this in the first move, then player 2 wins immediately. If he goes here, then player 2 goes here, and now depending on whichever one he goes, 5 or 7, player 2 has a response, right? So this shows that player 2 has a winning strategy. So the question is, given a graph and given such arrows, does player 1 have a winning strategy? Right? So with a designated start vertex, so in here, this is the designated start vertex. So how is it related to geography? Right? So geography was like naming some places, etc. Because if you give me a dictionary of names of places, I can, let's say, fix a starting word, right? And then I can, because I know the relation, right? And the goal is to not repeat a place. So like here we cannot come back to the same vertex. So so once you have the list of places, so I have the name Hyderabad. So now I know the next place has to be Dubai, Delhi, Denmark. I don't know what other places that name, like Dhaka, that starts with D, right? So I know the arrows once I know the names of the places. So a fixed list and the spellings define the graph for me, right? So the question is, does player 1 have a winning strategy? And this happens to be a piece-space complete problem, right? In fact, many games are piece-space complete. So, right. So this is so I'll maybe write here. So generalized geography is piece-space complete. This is also TQBF is also piece-space complete. Right. So in fact, there are many games, many general version of games that are piece-space complete. For example, you can define a generalization of the game chess, right? So chess is played on an 8x8 board, 64 squares, and with 16 pieces each side to begin with, so 32 pieces overall. It's a finite game, right? Because there are rules of the game. Let's say if you repeat the same position 3 times, then it's a draw. Or if you make several moves without a capture or a pawn moving, then it is a draw, right? So there are rules that kind of enforce some progress, which means the game will end after a while or after some fixed number of steps. So chess is a finite game, so there is you cannot really ask if chess is like piece-space, if there's a white win or the black win on chess or whatever. It's a very finite game. So it's like, the game tic-tac-toe, right? Like you have to put knots and crosses, and whoever gets one in a row, they win. So but then it's a finite game. Like you can draw the entire strategy tree very quickly. But so that's not very interesting because you can solve it. But the game tree for chess itself is very complex. But what I'm saying, it's very complicated. Even with the current computers, you cannot solve it. But the point is that it is finite, right? It is complex, but it is finite. But you can define a generalized version of chess, like played on an n by n board with, let's say, 2n by 2n pieces or something. And such a variation has been shown to be piece-space complete. So a generalized chess, which is general chess, where the board size keeps increasing, etc. And you can, let's say, similarly define rules. That is piece-space complete. And several games like this, like generalized checkers, that has also shown to be piece-space complete. Many games that are popularly known has been shown to be piece-space complete. So that is what I want to say about piece-space complete. This is something that we already discussed, like a listing of classes. And yeah, that's all I wanted to say in this lecture 60, right? So basically 2 points I wanted to mention that we did not cover in detail, or we could not cover in detail in this course, which is but which appears in chapter 8. One is NL equal to co-NL and piece-space completeness. So do read the book for the full proofs of piece-space completeness of these languages like TQBF and generalized geography, etc. And also for the proof of NL equal to co-NL. Of course, you can also refer to other material if you find other convenient material outside. And with that summary, we come to the end of chapter 8, right? So we couldn't fully cover chapter 8 because we only devoted 1 week for chapter 8, right? But there are other resources available where you can refer and learn, right? And so in chapter 8, so far we saw space complexity, relation between time and space complexity. We saw NL, we saw L, we saw NL completeness, we saw Savage's theorem, and we saw the summary of these results. And that completes the chapter 8. And that also brings us close to the end of this course. And we will do just one more lecture summarizing what we have seen throughout the course. So that will be also the last lecture for this course. As far as lecture 60 is concerned, we'll end now. So thank you, and see you in the next lecture 61. Thank you.